Good morning, everybody. Thanks for coming, guys. Gayatri was first in the room. Well done. Jack's like, oh, man. Jack, you're always so close. Come on, I believe in you, Jack. You can do it tomorrow. Just well done. Jack's like, oh, man. I love, and then Jack's done a crying face, but a smiling crying face. I believe in you, Jack. Tomorrow's your day. I can feel it. I can feel it. Right, let's crack on, guys. Share screen. Before I do that, what I'll do is I will take my learning objectives out of my thingy links, my YouTube link, put that there, and then I'll also take the title as well. It's always good to have consistency. That's not doing what I want to do. Hang on a sec. So this is iGCSE Acid-Base Theory, Lesson 2. Doing well. Cracking on. Boom. There we go. Reactions and their salts. I like it. I like it a lot. Right, let's go. I'm going to close down. Going to pop out my chat in my little YouTube chat. Pop out chat. And then get rid of my YouTube channel. Save some bandwidth. Gone Yorkshire. Oh no. Right. Okie dokie. And then I'll switch over to my clip cam. Boom, boom, boom. Getting there. There we go. Woo! There. Up and running. Okie dokie, guys. I'm just going to tilt that a little. It's probably better. There we go. Okie dokie. Let's close that down. Right, guys. This is my lesson. Okay, so we're on acid-base theory, lesson 2 for GCSE year 10. Fold my laptop down to be a tablet. Now, last lesson, just nice to do a bit of a review of last lesson. Last lesson, we were doing the key stage 3 revisit. And we were looking at the acid bases, the properties that we need. I didn't add in the properties, by the way. I didn't add in the hazard symbol for alkalis, which is the same, by the way, which is corrosive and irritant. But it was nice and then we did a whole load of lovely equations. It was nice to see the alkali metals appearing. And then I gave you your 4 indicators for GCSE, which is really nice. I felt like it was a good lesson yesterday. But we didn't get up to the acid-base reactions. So that's today's lesson. So let's move on to today's lesson number 2. And our learning objectives are, so number 1, you need to know your reactions. Now, I've already taught you these reactions when you come into GCSE with me at the start of year 10. The first thing I do is give you actually these set of reactions. And some of you might remember these, and they're so important in chemistry because, like, one of the most common question I have at A-level, it's not even a question, it's a statement. It's, Mr. Duncan, I don't know what I am making. And the only way, and one of the best rules, or some of the best rules that you have in chemistry are the 3 that are now about to appear. There are a whole series of methods of being able to know what you make. The first one is obviously swap the non-metal or swap the metal. Doesn't make any difference which one you do. That's a standard displacement reaction. Then, of course, you've got your combustion rules. Then you've got your acid-base rules. So you learn the rules, these generic set of rules that allows you to be able to get some information out. Lots of students always go, why don't we make anything strange? And I'm like, that's one of the beauties of chemistry. It's the fact that there are rules to this. You know, you always tend to make certain products because certain products are more stable. I just received an email. Sorry about that, guys. Oh, no, it's just me stating that I've got information about a Google Meet that I've had. Okay, so let's start running through these. Jack, have you managed to get all your learning objectives in? I tried to keep my learning objectives as short as possible. So my first one, know your reactions. Number 2, be able to name your salts. And number 3 is be able to write equations. Now that one, of course, is going to link heavily to my formulae. Now, formulae is something that we cover at the start of year 10 again. And so we'll see some overlap with those. Okay, so let's pick up our acid-base rules. Oh, I need my little fan. My little fan's there to keep my laptop cool. Yeah, I mean, obviously it's just not as cool as me, but it is needed. Just otherwise, my my little laptop overheats. Okay, so these are, I like to call these acid-base reaction rules. Acid-base reactions rule. See what it did there. See what it did. Acid-base reactions rules. Okay, so acid-base reaction rules. So there are technically 4 rules, but we combine 2 of them. So the first one is MASH. Number 1, metal plus acid. Complete on the chat, please. Complete the equation. Metal plus acid goes to blank and blank, please. Complete. Next, number 2. Metal oxide. Metal oxide plus acid goes to blank plus blank. Number 3, metal hydroxide. I'll give you an example of each of these in a second. Metal hydroxide. Salt plus hydrogen. Thank you, Zina. Well done. Salt plus hydrogen. Like it. I'm sticking with my words, by the way. Yeah, well done, Zina. Well done, Jack. Good man. Well done. So metal hydroxide plus acid goes to blank plus blank. And I'm now going to do this. I wonder if anyone can figure out why. Number 4, metal carbonate. Metal carbonate. Carbonate plus acid. Gone Yorkshire again. Metal carbonate plus acid goes to blank plus blank plus blank. Right. Same output. Same outcome. That's the 2 we linked together. Well done, Jack. Jack's on it today. Salt plus water. It's French for water. If you're interested, just ask Lauren. Salt plus water. There we go. So what about number 4? So do you now see that there are 4 rules, but only 3 rules? Wait, that's 3. Yeah, it is 3. Yes, absolutely right. Jack, they're both 3. 3 and 2 are the same output. I'll explain why in the equations in a second. So the question is, can anyone give me number 4? Now, I'm hoping you're going to also realize why I give you them in this order. Salt, water, CO2. Thank you very much, Zina. Salt, water, plus carbon dioxide. Carbon dioxide. So I'm giving you them in this order because you can see like an evolution in the process. Oh, they're both? Yes, they're both water. Let's look at the equation now. Let's look at an example of each of these in an equation form. So let's go for magnesium plus HCl goes to. So now this becomes much more, you realize that these are called generic equations. You'll never be asked to do these at GCSE. This is key stage 3, and then it drops to key stage 4 when all of a sudden you're doing this. This is much more challenging. Now, magnesium is, of course, a metal, so it's a solid. All acids are aqueous. All acids are aqueous. What am I now going to make, please, on the chat? Now, this is now what we realize in my learning objectives. The question I have just asked you, we know the generic outcome, salt and hydrogen. So we know one of them, but then can we translate that out into an equation? What we realize is we have gone from the reactions, which we have now finished. We know the reactions. What we now need to be able to do are these 2. We need to be able to name the salts. Oh, that's blue, that's just too blue. Name the salts and write an equation. So I've given you this one, and the question is, can anybody give me, I don't mind you if you give it to me in words. I don't mind that. Magnesium, chloride, and hydrogen. Thank you very much, Zina. So I'm going to get, so she's just named the salt and used the reaction type to be able to give me the products. So I'm going to get magnesium chloride, MgCl2, and H 2. We know that hydrogen, any words that end in "ene" or "gen" are going to be diatomic in their symbols. So do watch out for that, or in their formula. I shouldn't say symbols, formula. So now I need to balance it, and that now balances. Magnesium chloride, of course, will become aqueous because it's going to dissolve in the water. Well done, Lauren. Lauren, check the formula of your salt. And the hydrogen, of course, is going to be a gas. My observations here is going to be the metal's going to vanish because it goes from a silver shiny metal to becoming a colorless solution, and we're going to get fizzing, effervescence. But would you have to balance it up? Of course. Well done, Zaina. Good job. So these equations, what you realize is this here, these reactions, so it's a funny set of levels, because what you realize is the generic equation here is a very low level, key stage 3. You're talking about a level 2. Yeah. But then the level 2 then requires you to know all 4 different ones. So an individual equation might be level 3 or level 2 even, yeah, from key stage 3, but then knowing all 4 of these now becomes a level 4, knowing all 4 of them, yeah, but then being able to write your equation from your base reactants, acid base reactants, you're talking now up to a level 7. So it's nice that to see how this evolves through chemistry, how one particular topic, which we started in year 7, can I just point out what you were given in year 7, just to show you the year 7 bit. In year 7, we were given acid plus base equals salt plus water. And they were actually given alkali, but I don't like that. Acid base is salt plus water. That's what you were given at key stage 3. Now, what we realize is that that's not always true. That now evolves into these 4 at key stage 4. So this is key stage 3, which is now officially dead. Yeah. Now, guys, I'm very sorry at that point. I need to admit something here. And the admittance is, admittance, not a word, I'm confessing here that this equation, which is given in key stage 3, it's not exactly a lie. Because the reason being is it does apply to the 2 in the middle. Yeah, it applies to 2 and 3. But the problem is it's not complete. Yeah, at key stage 3, at year 7, we don't want to give too much information. It's an awful lot as it is, especially when they're coming from primary, where they've done no science at all, to secondary, where they're doing a lot of science. So we keep it simple, but this is now dead for key stage 3, and you now pick up these 4 new rules, which are the expansion on what you had at key stage 3. And these are much, much harder. And then when you drop that into a calculation, that takes it then to a level 8, 9. So we've got a metal plus acid, salt plus water. Let's now do the metal hydroxide, and let's keep some similarities here. So let's do magnesium oxide. Once again, we've got to consider the formula. Yeah, every time we're generating a formula in chemistry, we must consider the process of how we're building it. So just to explain this one, magnesium we find in group 2 on the periodic table. Let's have a look at what that looks like. There's the A-level table, don't want that. So we know that magnesium is in group 2. What that means is it's going to therefore be +2 in its ion. Chloride is in group 7, so therefore going to be 1-. We get +1, +2, +3, nothing. -3, -2, I don't like that. I'll flip it over at that point. You can put the charge on actually on either side, just so you know. What I will do though is keep some continuity here. +1, +2, +3, nothing. -3, -2, -1, nothing. So we learned that also magnesium is a +2, Mg +2, Cl is Cl1-, and then we do the stupid cross and down trick, which I don't like, but what we realize is we need to cancel out charge. The formula of any compound is due to the ions cancelling out each other's charges. So if I have 2 Cl minuses, the charges now cancel out, and I end up with the formula of MgCl2. Some people learn what's called the X factor trick, which I really don't like. They bring the numbers down. So the invisible number 1 drops into here, yeah, and the 2 drops in there. The charge is then, the actual plus or minus disappears, but I don't like that because of magnesium oxide. Magnesium oxide is made from Mg2 plus and O2 minus. We know this because magnesium is in +2 and oxygen is in group 6, which is -2. So we cross them down and you'd get Mg2O2. Well, that's not correct. That won't happen. The reason being is the charges simply cancel out in the first place, so it simplifies down to simply being MgO. So we're running every time I write a formula, I'm considering that process. And I'm doing it, I do it super quickly because I've been doing it for years. The more you practice, the more you do this, the faster this becomes. By the time you get to A level, you're doing it pretty briskly. So I've got magnesium oxide. Let's add it to hydrochloric acid, HCl. Right, this time I've got metal oxide plus acid. The acids are always aqueous. Magnesium oxide is a solid, being ionic. All ionics are solid as room temperature. Right, they're going to react together and I'm going to get salt and water. My salt is magnesium chloride, the same formula that I had before. That's now aqueous. And I'm going to now get water, and I need to balance it. 1 magnesium, 1 magnesium, 1 oxygen, 1 oxygen, 1 hydrogen, 2 hydrogens. Double it. 2 hydrogens, 2 hydrogens. Yeah, 2 chlorines, 2 chlorines. I'm good. Yeah. So it's nice to see the process. These all take practice, and this is going to be your homework, year 10. So I've got a sheet which is entirely made up of these equations, where what you do is some of them you'll get the start and the product, and then you'll have to reverse it. I'll show you that now. Anyway, you're going to get a whole series of these equations for homework. So that now explains why we don't get hydrogen, because the hydrogen is now bonding to the oxygen to form water. Sir, then would it be okay to do the X trick as long as you simplify the powers after? Yes, Jack, that is absolutely fine. That is okay. I'd prefer you to think in terms of charges, Jack. The charges has more value, in my opinion, because in reality, the X factor is not a real thing, is it? It's just it's a trick. It's not an explanation as to why it's happening, whereas the charges is a true explanation. Jack, I'll give you another example. So if we did, let's do another one. Let's do chromium 6 plus and O2 minus. Yeah, the crossing down would be Cr2O6. Then you'd simplify it down to CrO3. Yeah, in reality, I see the 6 plus. I need 6 minuses. How do I get from 2 minus to 6 minus? I'm going to multiply it by 3. Yeah, but yes, Jack, that's absolutely fine. Totally fine. Totally fine. Next. Okay, let's now try something a bit more interesting. You can pause the video, guys, if you want to have a go at this in a second. You can just, so let's try this. Blank plus blank goes to, let's go calcium bromide and water and CO2. Right, so the question is, if this is an acid-base reaction, now I'm going to ask Jack this specifically. Jack, I'm asking you this because you were the one in the last lesson who asked about the hydrogen halides. You were the one who was like, hang on a minute, can we actually get other acids in the group 7s? So Jack, the question is, what acid did I use? And what base did I use? Now, Jack, consider the general equation. Which one of these am I using for question number 3, for this question here? I'm curious just to see if you can figure this out. It's quite clever. Chemistry is good in this. It's all games. It's all games. Puzzles and games. I'm having a green tea and ginger, being proper healthy. Yeah. Well done, Jack. It is number 4. Well done. So Jack has correctly identified, because of the carbon dioxide, that it's number 4 that we're using. Now, Jack, can you reverse the equation and tell me the acid and the base? Who was my acid and who was my base? I know you can do this, Jack. Come on. Come on. Whilst Jack's thinking about that, I just want to quickly point out to everybody that we are now, because the rules is easy, I gave you the rules. We are now working towards the naming salts and equations. Both of these learning objectives we are now doing for the whole rest of the lesson. By practicing equations, seeing the routines, and understanding what's going on. Jack, you can pass if you like. Okay, I'm going to give Jack the answer. Gayatri, well done. So Gayatri has realized that the metal in the salt, the metal in the salt must have been in the base. And that to form CO2, well done. Oh, Jack, so close. Check your carbonate. Yeah, it's actually CaCO3. And well done for identifying the acid, Jack. Good man. And he even balanced it. Well done. So it was hydrobromic acid that I used. The Br from the acid moves over into the salt, and the metal moves over into the salt. Yet carbonates are always CO3. The carbonate ion is CO3 2-. We'll do that now. We can add that into our notes as a recap again. So guys, now my year 10s will be getting super sick of this, guys. But for those people who are new to my channel, this is one of the most important things I can ever teach you in the history of chemistry, from GCSE onwards. Yet the complex ions. So we have the nitrate ion. They're going to be so fed up of this. Year 10s, please copy it in. It's always good to recap these. Nitrate, NO3 1-. Hydroxide ion. Hydroxide ion. OH-, 1-. Next one, carbonate. Carbonate ion. CO3, 2-. Sulfate ion. Sulfate ion. SO4. SO4 2-. I'm getting ahead of myself. Oh, I forgot the oxygen in water. SO4 2-. Last one, phosphate ion. Phosphate ion. PO4 3-. Now that one technically isn't GCSE, but I always add it in anyway. The next one is the positive ion, which is the ammonium ion. I cannot stress the importance of these ions. Ammonium ion. Yeah, ammonia is a gas. Ammonium is an ion, NH4+. Yep. These ions, guys, you've got to know. Yeah, it's so important. So, nice this. So what we now need to do is we've picked up our complex ions. By the way, other ones that are important. Silver is always +1. I'm going to add these on as well. Silver ion, always +1. There is actually a time when it's not, but you need to learn at GCSE that it's +1 always. Next one, lead, 2+. Pb, 2+. Then we have mercury. Mercury ion, Hg, 2+. There we go. You need to know all of these, guys. All of these. There we go. Learn those tables. These are the complex ions. And you've got to learn them. Learn. I gave you this at the start of year 10, explained to you how important it was. Without these, you cannot build any of your equations. Yeah, it's so important. Cannot stress the importance of that in chemistry. Right. So now that we've done that, let's get the rules for salt naming. Let's put salt name rules. Okay. So the salt name rules, what about zinc? Always 2+. Always 2+. Zinc is always 2+. You can add that in too. Zinc ion is Zn2+. What we realize is all these extra ones, mostly 2+, except for silver. But thank you for adding that in, Jack. Thank you. Salt name rules. So we've got, if I use, so this is a table. This is, I'm going to change my color. Acid used. Acid used. So we've got hydrochloric, HCl, HNO3, H2SO4, H3PO4, and also vinegar. This one's the tricky one. This is ethanoic acid. Ethanoic acid. You'll understand why I've underlined the ic acid. You'll understand why in a minute. Go away. There we go. So if I've used this acid, what salt will I get? So this is now going to be my salt name. And salts, of course, are neutral. So we can go salt name, ... So we've got X chloride. Yeah, X chloride. So hydrochloric acid will produce a chloride salt. Let's get rid of that. Yeah, it's a chloride. Now, if you're wondering what the X is because in a salt, there must be a metal joined to it. This could be sodium chloride. In order to make sodium chloride, you can use hydrochloric acid. Yeah? Okay. Okay. Next one, which is going to be X nitrate. Yeah? So if I use nitric acid, I'm going to form X nitrate. So if I made sodium nitrate, I used nitric acid in the making of it. Next, X sulfate. So if I used sulfuric acid, I'm going to make a sulfate salt. So if I had sodium sulfate, the acid used was sulfuric acid. Next, X phosphate. If I have a phosphate salt, sodium phosphate. Let's do the examples. NaCl, hydrochloric acid used. NaNO3, nitric acid used. Na2SO4. Yeah, I used sulfuric acid in the making. Na3PO4, sodium phosphate. If you're wondering how I have built them, Na is +1 from group 1. Chloride, 1-, cross and down or cancel charges, NaCl. Na +1, nitrate, NO3, 1-. The charges cancel, NaNO3. Sodium +1, sulfate, SO4, 2-. I need 2 pluses to cancel out the 2-. So I now need, so I'm going to multiply by 2. It now cancels, and I get Na2SO4. Next, sodium phosphate, sodium +1, phosphate, PO4, 3-. I'm going to need 3 of those to cancel out the negative charge. So I'm going to end up with Na3PO4. Yeah, you get the point. Next one. Now, this one's kind of important because it's kind of new to you guys because you guys haven't done organic yet. So this one is going to be X ethanoate. Ethanoate. I know it's horrible. I apologize. This would be sodium ethanoate. And yes, it's very odd. It's very strange. The Na goes afterwards. Can I just point out, they wouldn't actually penalize you if you did it differently. If you did it like this, they actually wouldn't penalize you. But I wouldn't do it because it's just, yeah. Sorry about that. It's a very odd one, sodium ethanoate. Yeah. Just to explain why, because ethanoic acid looks like this. This is what ethanoic acid looks like. Now, the ethanoic acid has 4 hydrogens, but there's one special hydrogen, which is him. He's all on his own, and he looks different from the other guys. Now, we're not being racist here or anything about him looking different, far from it. In fact, looking different makes him special. He can do things that the other hydrogens can't do. For ethanoic acid, why is it instead of, yeah, good question, Julius. Julius, because it is. It's because Julius, the reason being is because of the type of formula I'm writing, Julius. So if ethanoic acid, which is this guy, you could write its molecular version, which would be C2H4O2. That's its molecular formula. This is the actual number of atoms of each element in a compound. But the problem is that doesn't tell me anything about it. Yeah? So what that means is I then turn it into what's called structural, which is CH3COOH. And that structure there, all carboxylic acids are pigeons. That structure there literally translates to carboxylic acids. It's carboxylic acids. I'm trying to think of an example. It's because it's telling us about it. That's why. And I know that sounds really strange, but it's telling us the structure. It's telling us how to draw it, Julius. Sorry about that. It just is. Anyway. Now, ethanoic acid can lose this hydrogen. This is the hydrogen it can lose. Is it because when you separate it? Yes, kind of. Yes, kind of. Yeah, you get 3 different structures. Sure. Yeah. That's as good an explanation as anything, Jack. For the main bonds. Yeah, Jack, it's not really to do with that. Okay, I'll give you another example. Another example of this. I don't want to go too much out. This is going way off piece now, guys. Here's another one. This is an aldehyde. Yeah, this is an aldehyde. This is ethanol. I'll be teaching you these soon in organics. So this is ethanol. F means 2 carbons. I can color code this. Eth means 2 carbons. Next is an. F, an. And an means carbon-carbon single bond. And then this whole structure here tells us aldehyde. That's an al. It's the aldehyde. And if you write that as a structural formula, it becomes CH3CHO. It's a CHO. And the reason you wouldn't write COH, because that now looks like an alcohol. The way that we organize things tells us which family it is. It's awkward. I know, it's tricky. You'll learn that in organics later on. So this would be sodium ethanoate, by the way. Now, all of these come up at GCSE a lot, these naming salts. And it comes up quite a lot. Can I just point out, there is a level 8-9 here, guys. The level 8-9, love 8. Love 8-9 is this guy. Yeah, it's knowing that ethanoic acid becomes an ethanoate. It's the complication in the name that gives it the really high level. Can't really tell you why. It's like anything else. You learn the names of something, but it's a level 8-9. Very few people tend to get it. It's because I think what happens is you learn these quite early on in chemistry. You get these a lot. These are repeated in the process, yet taught early. Taught early. Yeah, and this is taught late. This one's taught late, which means it just tends to be less common that people get it right. Go figure. Right, now I'm very aware of the time, folks. So we now have our salt name rules. We've picked up all of our salt names. What we now need to do is we need to practice writing our equations. And I think at this point, I'm actually going to end my lesson. I think what we need to do is I need to give you the homework of using these rules, writing these equations with the formulae and practicing it. And I'll go through those then at the start of next lesson, which is tomorrow. So, okay, guys, I'm going to end the video here. Is everyone okay with this so far? Let's get rid of my stop sharing screen. Get my camera back to my front, not my rear. Let's go to my front. There we go. Right, guys, I'm going to leave you there for today. I will post the homework on the classroom. It will take practice. I'll start off easy, giving you maybe just 10 questions, trying to make sure I hit every one of these acid-base reaction rules you can apply. Yeah, but I will leave you there, guys, for today. When is the homework due? That's a good question. I don't want to give you just 24 hours. It's obviously mean for me to do that. I'll say for next Tuesday. Makes sense to do that. Right, guys. I'll see you all soon. Bye now.